Dedekind cuts gave us a complete ordered field, but we still owe one very specific identification. We will prove that the cut built from rational squares below 2 is positive and has square exactly 2. Then we will compare the Cauchy sequence construction and define complex numbers whose relationship with order is less cooperative. Let R be the Dedekind cut D sub 2, containing every negative rational and every rational whose square is below 2. Our goals are R greater than 0 and R squared equal to the embedded rational 2, namely 2 hat. Real numbers are cuts. So proving R squared equals 2 means proving the product cut D sub 2 squared equals 2 hat. The real 0 is 0 hat, the cut containing exactly the negative rational numbers. Every negative rational belongs to D sub 2, so 0 hat is contained in D sub 2. The containment is proper because 0 belongs to D sub 2 but not to 0 hat. Since the real order is inclusion, D sub 2 is strictly greater than real 0. Thus R is positive. The difficult step needs this lemma. Every rational q below 2 lies below some rational square that is still below 2. We will prove it without sequences or limits. Set epsilon equal to 2 minus q. By the Archimedean property, choose a positive integer n with 5 over n below epsilon. Now inspect the finite grid 1 plus 1 over n through 2. And record the indices whose grid points have square below 2. The index 0 qualifies because 1 squared is below 2, while n does not because 2 squared is 4. Thus the displayed finite set is nonempty. Because f sub n is a nonempty finite set of integers, it has a largest element m. Let t be the corresponding grid point. The maximum lies between 0 and n minus 1, so t is rational and lies between 1 and 2. Membership of M says t squared is below 2. Maximality says the next grid point cannot also have square below 2. Therefore t squared is below 2, while t plus 1 over n has square at least 2. No infinite process has appeared. Finite sets remain pleasantly mortal. The square gap from t to 2 is no larger than the change in square produced by one more grid step. Expanding that change gives 2t over n plus 1 over n squared. Since t is below 2 and n is at least 1, this is below 5 over n, which was chosen below epsilon. Thus 2 minus t squared is below 2 minus q. So q is below t squared, while t squared remains below 2. The lemma is proved using only a finite maximum, the Archimedean property, and elementary inequalities. Because d sub 2 is positive, its square uses the non-negative cut product formula from P17. Take x in d sub 2 squared. If x is negative, then x is automatically below 2 and belongs to 2 hat. Otherwise x equals ab for non-negative a and b in d sub 2. So a squared and b squared are both below 2. Then x squared is below 4. Since x is non-negative, x at least 2 would force x squared at least 4. A contradiction. Thus x is below 2 in every case, proving d sub 2 squared is contained in 2 hat. For the reverse inclusion, take any rational x below 2. If x is negative, it belongs to the negative rational part of d sub 2 squared immediately. Now suppose x is non-negative. The finite grid lemma provides a positive rational t with x below t squared and t squared below 2. We will factor x as t times x divided by t, then verify both factors belong to d sub 2. The first factor t is positive with square below 2, so it belongs to d sub 2. Because x is non-negative and smaller than t squared, division by positive t gives x over t between 0 and t. Since D sub 2 is downward closed and contains t, it also contains x divided by t. Thus x is a product of two non-negative members of D sub 2, so x belongs to D sub 2 squared. Together with the negative case, this proves 2 hat is contained in D sub 2 squared. The two inclusions give D sub 2 squared equal to 2 hat. Therefore r is positive and r squared equals real 2. This positive root is unique. If another positive s has square 2, then s minus r times s plus r equals 0. Since s plus r is positive and therefore non-zero, the field has no zero divisors. So s minus r must vanish. Thus the cut D sub 2 is exactly the unique positive real number called square root of 2. Similar cut-level arguments can construct further roots, exponential functions, and logarithmic functions from scratch. But each construction needs new proofs of existence, uniqueness, monotonicity, algebraic laws, and compatibility. That route is rigorous and spectacularly inefficient, so it is not recommended here. Near the end of the basic series, we will have enough theorems to treat these functions far more cleanly. There is another standard construction of the real numbers using rational Cauchy sequences. A rational sequence is Cauchy when, for every positive epsilon, all sufficiently late terms are within epsilon of each other. The truncations 1, 1.4, 1.41, and 1.414 illustrate the intended behavior. This matches the familiar intuition that an infinite decimal is a sequence of increasingly accurate, rational approximations. Two rational Cauchy sequences are declared equivalent when their termwise difference tends to 0. A real number is then an equivalence class of rational Cauchy sequences. Addition and multiplication are defined term by term and then passed to equivalence classes. Constant rational sequences embed Q, and the resulting complete ordered field is isomorphic to the Dedekind cut construction. The Cauchy construction better matches infinite decimal intuition, but its details create a different bureaucracy. One must first develop Cauchy sequences and prove the displayed relation is an equivalence relation. Then addition, multiplication, order, inverses, and every comparison must be proved independent of representatives. Finally, one still proves the quotient is complete. Apparently, changing construction methods does not repeal proof obligations. The method is important and elegant, but we will not build the real numbers a second time here. For present purposes, define the complex numbers as ordered pairs of real numbers. Write the pair a, b as a plus bi, where I is 0, 1 and satisfies I squared equals -1. Addition is component-wise, while multiplication is defined by AC minus BD, AD plus BC. These operations make C a field containing a copy of the real numbers. Complex analysis will demand much more, but not from this video. Suppose some total order made the complex numbers an ordered field. For non-zero z, either z is positive or negative z is positive. In either case, z squared is a product of positive elements. Since I is non-zero, I squared must be positive, but I squared equals -1. So -1 would be positive. Also 1 is a non-zero square. So 1 is positive. Adding -1 to 0 less than 1 gives -1 less than 0. -1 cannot be both positive and negative. Therefore no order can make the complex numbers an ordered field. The complex numbers can be ordered as a bare set in many artificial ways. None of those orders is compatible with field multiplication. The cut D sub 2 is positive. And a 2 inclusion argument proves its square is exactly the embedded rational 2. Equivalence classes of rational Cauchy sequences provide another construction of the same complete ordered field. Complex numbers are real pairs with special multiplication, forming a field that cannot support any compatible field order. Different constructions change the paperwork, but every claimed operation and property still demands proof. Next, we will discuss the axiom of choice and Zorn's lemma, two principles that turn existence proofs into a specialized art form. That episode will be the final installment of the preliminary series.